Have you seen the movie Interstellar? There is a planet near a black hole. 60 minutes on that planet are equivalent to 7 years on ordinary planets. Why? Because time dilates due to the gravitational field. Strong near the black hole. And with this, we've transitioned to the theory of general relativity, which I will present in several episodes following my book, Physics Explained. We will start with the essence of the theory, which can be understood starting from the equivalence principle. Maestro, roll the tape. Einstein developed the theory of special relativity in 1905. It is called that because it refers to inertial reference frames, which move relative to each other at constant velocity. In the following years, Einstein was interested in generalizing his theory to any reference frames, including those that accelerate relative to each other. This effort took over 10 years. The major difficulty was mathematical. In order to generalize the theory, Einstein had to learn a lot of mathematics, especially Riemannian geometry. He did all this patiently, learning at first from his colleague Marcel Grossmann. In 1915, he wrote to his friend Michel Bessot, right after he had done relativistic calculations for Mercury's perihelion, and obtained the same value as the one observed experimentally. The most ambitious dreams are achieved with general covariance, Mercury's perihelion wonderfully precise. The key term is general covariance. That means you can use any reference systems, even ones moving with acceleration relative to each other. The major surprise for anyone learning general relativity is that this theory is essentially an improved version of Newton's gravity. That's why today general relativity and gravity theory are considered the same. That's why our journey will start with gravity. Grazie. When something falls from our hand, we always look down, never up. Why? Because things aren't attracted to the ceiling, but to the ground beneath us, as Newton says, through a gravitational force of attraction. The problem with this force in Newton's theory is that the force is instantaneous. In other words, it's not possible for one body to instantly attract another body that's thousands of light years away. If that were the case, then we could instantly transmit information to the other one. At the edge of the universe, moving a body back and forth and measuring the variation of force billions of light years away. Newton noticed this, but he didn't have a solution. The physicists after him tried to extend the law of gravitational attraction by considering a finite speed for the propagation of gravitational interactions. They started by introducing the gravitational field of a massive body, defined by analogy with the electric field. The force with which the massive body attracts? The gravitational force on a test body was taken to be proportional to the mass of the test body and dependent on the gravitational field of the massive body, similar to the electric force. In the new theory, the variations of this gravitational field are transmitted step by step at the speed of light, just as the variations of the electric field are also transmitted step by step and also at the speed of light. We won't discuss this theory, as it's only an approximation of Einstein's theory. It is enough to say that Einstein sought to generalize his theory to non-inertial reference frames. That is, if these appear naturally in the presence of gravitational fields where bodies are accelerated by gravitational forces. But where should the search begin? Well, sir. The reason why Einstein stubbornly believed that gravity plays a special role is found in Newton's thinking and experiments. Thus, Newton understood that his theory had a special aspect that he could not explain: the equality between inertial mass and gravitational mass. The inertial mass of a body is defined as the ratio between the force applied to a body and the acceleration that this force gives to the body. A equals F divided by m. It appears in experiments without gravity's influence. On the other hand, gravitational mass is defined as the ratio between the force F with which the body is attracted by the Earth if it were placed on its surface, and a universal constant g, which represents the acceleration with which all bodies fall at the surface of the Earth and which has a value of 9.8 meters per second squared. That is, the gravitational mass will be m, which is equal to F divided by g. The two values of mass, inertial mass and gravitational mass, have received different names because they are the results of different types of experiments. As you can see, the first experiment involving inertial mass is dynamic. The bodies move because we pull them. And the second experiment, which involves gravitational mass, is static and involves gravity. The Earth pulls on the body. The equality between inertial mass and gravitational mass then highlights an intrinsic relationship between the motion of the body and gravitational forces. It tells us that a body that is harder to accelerate with a greater inertial mass will also weigh more with a greater gravitational mass. It could have been otherwise, why not? That's why if we let a body with twice the gravitational mass fall, the Earth's gravitational pull will also be twice as strong. However, the acceleration during the fall will remain unchanged because this double force is divided by the inertial mass, which is also doubled. Thus, all bodies fall with the same acceleration on Earth if we neglect air resistance, regardless of their mass. This can be seen in this wonderful experiment from BBC, where they dropped a feather and a hammer in a vacuum chamber. You can see them fall together at the same acceleration. And yet, Einstein said, why don't bodies fall differently in the gravitational field if they are all different? In an electric field, for example, some objects accelerate more, others less, and some not at all, depending on whether they have electric charge. In a gravitational field, however, everything falls the same way, no matter what they're made of. So what determines the motion of that body if its internal structure doesn't matter? If the motion has nothing to do with the body itself, because all point-like bodies fall the same way under ideal conditions, then what could it be? It could be about what is around the body. But what is there, since it's just empty space? We're getting closer to the answer. Here is Einstein in an elevator, where he is doing all sorts of mechanical experiments, unable to look outside through a window if there were one to see what is happening with the elevator. Another person, up to some mischief, either puts the elevator in zero gravity or lets it fall freely in Earth's gravitational field. The question is, will Einstein know which of the two situations he is in? Let's take the second situation, the elevator in free fall. Not only is the elevator falling, but all the objects inside it are as well. Because of the equality between inertial mass and gravitational mass, the fall of the objects will be synchronized. Suppose Einstein drops an apple as the elevator free falls. Both the elevator, Einstein's hand, and the apple will fall in sync due to the equality of inertial and gravitational masses. That's why Einstein will notice from inside the elevator that the apple stays next to his hand, even though he let it go. A similar situation occurs on the International Space Station, when astronauts let go of objects from their hands. Many people mistakenly believe that the astronauts on the station have reached a weightless environment, which is why they float in space. In reality, however, this is not the case because the International Space Station orbits just 400 kilometers above the Earth, a much smaller distance than the Earth's radius, which is almost 6,000 kilometers. This means gravity there is about the same as on Earth's surface, the station. So, why do cosmonauts float freely in the space station? The reason is that the International Space Station is like an elevator in free fall all the time, orbiting the Earth in this way. It is a model for Einstein's elevator. Here's another example, this time a measurement I made. Here you can see the acceleration measured by an inertial sensor when the sensor was thrown straight up by me without introducing any rotations. At the beginning and at the end, the sensor's reading is equal to the gravitational acceleration, which is g 9.8 meters per second squared, because the sensor is almost stationary and measures the Earth's gravitational field. In the middle of the figure, the sensor is in free motion through the air. Now the measured acceleration is 0, even though the sensor is both going up and coming down. We can confidently say that the sensor believes it is in a weightless space, pay attention, both when going up and when coming down. An observer inside an elevator cannot notice the difference between two situations, free fall or weightlessness, just by looking at the objects inside the elevator. In both situations, the objects appear to be weightless, just as seen in footage from the International Space Station, which is constantly in free fall during its orbital motion around the Earth. But here is the key question. Is it possible for the situations to be identical in every respect? That is, not only mechanical phenomena, but also electrical ones or magnetic? All phenomena. What do we know now, and what will people and extraterrestrials discover in a million years? Albert Einstein, under the influence of the theory of special relativity, assumed exactly this. Namely, that the two situations, the one in which the elevator is in freefall and the one in which it is in a weightless environment, are equivalent in all respects. By performing any kind of experiments inside the elevator, we cannot determine which of the two situations we are in. The result is known as the equivalence principle. However, Einstein says we should compare something more unusual in the two situations: the structure of space-time. We discussed this structure within the framework of the special theory of relativity, that is, in a weightless environment where inertial reference frames can be constructed that move at constant speed relative to each other. We saw that this structure is Minkowskian. Basically, we have a relationship for the relativistic interval between two events that is similar to the Pythagorean formula, where only a few signs are changed. Let's go back to the observer in the freely falling elevator and note that his situation is equivalent to that of the elevator in weightlessness, far from the gravitational field. In the second case, however, far from gravitational fields, the structure of spacetime, its metric, is Minkowskian. Then, if the observer in the freely falling elevator sets up his own space and time coordinates, the spacetime he observes will also be Minkowskian. In other words, being inside the freely falling elevator, we will fully verify the laws of special relativity. This is even though we are in a freely falling elevator in a gravitational field and not in weightless space, as we assumed when we first constructed the theory of special relativity. However, let's note that anywhere in a gravitational field, we can choose a freely falling elevator. We can then imagine all of space-time, even where gravitational fields are strong, as being made up of smaller local pieces where space-time is Minkowskian. What could be the structure of this space-time built from small regions where it is Minkowskian like pieces of a puzzle? The answer that Einstein found is the key to the whole story, and you can see it in this picture. It is based on the similarity between Minkowskian spacetime and Euclidean space, with one more ingredient added. As you can see on the left side, curved surfaces are flat in local areas, although at greater distances, the surface remains curved. On the right, I have generalized to curved spacetime. In small local regions, spacetime is Minkowskian, meaning it is described by the theory of special relativity, but over large distances it will be curved. For this, we need to develop the theory of general relativity. That's when Einstein generalized it. In the presence of gravity, we will assume that all events take place on a curved, four-dimensional spacetime, as shown on the right side. Locally, on small regions, we can choose a Minkowskian metric like that of an elevator in freefall. However, overall, spacetime will be curved. This is Einstein's key, the cornerstone, if I may say so, on which he built his theory of general relativity. Then, a formulation of the equivalence principle could be this: under gravity, all events take place in a curved four-dimensional spacetime. Locally, the spacetime metric is Minkowskian. It's Minkowskian. We recognize the above principle every time we sit on the couch and let two objects fall. Neglecting air resistance, they will fall at the same time, no matter what they're made of. We can then choose a local coordinate system that moves along with the two falling objects. This is actually a local Minkowskian system. In this system, the objects that were initially placed at rest remain at rest relative to each other, which to us looks like the two objects are falling in sync. This is essentially the equivalence principle. More about its implications in the next episode. Until next time, please subscribe if you haven't done so yet by clicking this subscribe button right now. I thank those who support us on Patreon and those who become channel members here. Thank you also to the West University of Timisoara for their support. I am Christian Presura, Physics Explained. You are cool and I wish you all the best. Goodbye.